Welcome. Let me say something about functional on four manifolds, which I mentioned last time. It's a discrete version of the Regge calculus, actually quite natural in the discrete. So here is the framework. We work with the finite abstract simplicity complexes. This makes things a little bit more natural, especially the notion of duality. I mentioned if you have a triangle in a four manifold, then the dual space is a sphere, and so the triangle defines a sphere and the dual sphere is a sphere, and the join of these two spheres is the unit sphere. It's a three manifold. So the three manifold, the unit sphere in a four-dimensional manifold, is naturally just a join of a stable and unstable sphere. And what Regge did, he takes the triangle, takes functions on triangles. One function you can look at triangles is just the deficit angle on the dual sphere, which kind of can be expressed in the discrete just as the length or the volume of that sphere. So it's a natural functional, because we have this duality and because we have essentially we cannot make it simpler. So I'm interested in functionals which are simple and also where one can prove theorems. And the prototype of a functional on manifolds, of course, or simplicial complexes in general, is the Euler characteristic. It's natural because it is invariant under barycentric refinement, and there are nice theorems. My favorite, of course, is Gauss-Bonnet. This is, I think, also the most natural way to see Gauss-Bonnet-Chern, actually higher dimensions. This is becoming Gauss-Bonnet-Chern in two n-dimensional manifolds in the continuum, and it is just very natural using this generating function. The derivative at some point of that function is sum of the functions applied to the unit spheres. You cannot make it simpler. Unfortunately, don't have new results. It's kind of like von Neumann when he was giving a talk at the international conference once. In the middle of the talk, somebody shouted in Yiddish, "Alte Sachen!" And he was so humiliated, he left the conference pretty soon after. And indeed, he had no new results. He was working on something new. I don't want to compare myself with von Neumann, but sometimes you just don't have results. I actually was experimenting with this functional, and I wanted to have a result. I wanted to have something which you know, an identity, not just numerical results. You can do numerical results. You can say, okay, what is this functional for a given four manifold? I can compute that, but and then you would like to actually find some manifold where this is extremo, and that would be your Einstein manifold, a manifold which, you know, defines space and time. I don't know. So this is I'm actually more interested in theorems. Theorems like Gauss-Bonnet or the sphere formula, which is actually quite nice. If you take the unit sphere at some point and you sum up overall, you know, unit spheres, what you get is the sum over the even dimension and the sum over the odd dimension is the same. This is true for any network, any G. Also Poincaré-Hopf works in general. If you take a function on the vertices, which is locally injective in the sense that on every simplex it's injective, then it defines a total order on every simplex, and then the energy Wx, right, which you use for summing up all these energies to the Euler characteristic, can be applied to the maximal, the function where the function is maximal, which is a vertex, and then you get this Poincaré-Hopf indices, which in the continuum agree with the Poincaré-Hopf indices if you have a Morse function on a manifold. So that's pretty cool. And what I also did, about 10 years ago, is define this symmetric thing. So you can take the function and the negative function, combine it, average it, and what you get is then here Euler characteristic in the unit sphere of a submanifold defined by that function. So it's a codimension 2 manifold in a manifold, and for four manifolds it's just the unit sphere is a 3 manifold, a 3 sphere, and then in that 3 sphere, like our space is a 3 sphere probably, and then you have a 2 a two-dimensional manifold, which is the level surface of that function. And in the continuum, this can be kind of crazy, but in the discrete, this is always nice. This is always a manifold or empty. And so we can compute that, and we have then a curvature on two manifolds. We have also Gauss-Bonnet, right? And then so you can kind of see Euler characteristic as some sort of average overall kind of possible two-dimensional close to something which we see as intuition for scalar curvature. A scalar curvature is the average over all sectional curvatures over a two-dimensional space which is passing through that point. For each curvature, you can look at the average over all planes which go through some edge, which then defines a quadratic form or a two-tensor. So what we have here is kind of a very nice setup, and it works also in the continuum. So if you have a Morse function, you can actually interpret this index as an Euler characteristic, or 1 minus half of the Euler characteristic. Even-dimensional manifold, the unit sphere, is a 3-manifold which has Euler characteristic 0, so we get 1 minus the Euler characteristic of that 2-manifold, center manifold, divided by 2. So that's pretty cool. I think this Regge functional, has some potential to produce some interesting manifolds as critical points, especially if you look at this, soften the whole setup by allowing deformations. You can always take a probability space of functions, and then you can define also this volume can be defined integral geometrically, and so you can, when you define length integral geometrically, you can mimic Riemannian distances, Riemannian manifolds, and if you do that with the curvature, you get then the corresponding curvature. So, and then you can deform very easily in a probability space. These are weights, right? You can change the weights and see, continuously change the weights and see with the gradient method whether you get to a extreme. So you can apply machine learning to that problem once you are in an integral geometric framework. That's it for today. Alte Sachen.